But since we're already running a couple of minutes behind on schedule, I would like to introduce our next two presenters. They are two of our SmartThings PSRs, and they will give a presentation about Work Package 1. Claire and Sina, the floor is yours.
All right, okay. So thank you, everyone. I hope you can see my screen. Today, we'll be talking about the SmartThings approach to improved self-healing concrete, which is the work of Work Package 1, and that's supervised by Professor Ferrara. Okay, so let's first meet the Work Package 1 team. We're composed of 5 different ESRs. Firstly, Yasmina from the University of Ghent. Secondly, myself, Claire, from Micropore Technologies. Third, Mert from Avacom. Fourth, Harry from KU Leuven. And last but not least, Sina from Cardiff University. And today, myself and Sina will be presenting the work. So, of course, what is our problem? We have our aging infrastructure, which leads to the decreased safety to our population, an increased need for repair, and thus an increased need for investment from government and other funding bodies. How can we manage this infrastructure? We can, of course, go the conventional route by repairing our structures. However, this is often time-consuming and costly. We can replace and rebuild, but this damages our cultural heritage that we see within our structures, as well as creates nuisances in our day-to-day life. Something that we'll talk about today is monitoring and healing, so self-healing, of course, and this is the more innovative way that we can manage our infrastructure and assess our problem. So something that Professor Debele mentioned upon, but I'll further expand, is the biomimetic approach, where we take inspiration from the natural world around us and use it to influence how we make our processes and manufacture our goods. Within the self-healing industry, this requires the incorporation of self-healing and self-sensing materials into our cementitious matrix. Self-healing is myriad, and how we classify it is myriad, but the 2 main ways we like to refer to it is autogenic, which is less than 150 micron healing that occurs without any further engineering controls or addition through physical, chemical, or mechanical causes. And then autonomous, tackling cracks above 150 microns with the addition of any engineering additions or or materials. What we'll further be discussing today is mineral addition, capsular addition, as well as vascular networks. So I mentioned the biomimetic approach and how it can be compared to self-healing cementitious systems. Well, we can say that we all have a vascular network within us, making sure that we have oxygen and blood so that we can survive. Similarly, within a cementitious system, we can incorporate this vascular network, ensuring that self-healing cargo is transported throughout our matrix. Secondly, when we are sick or have an illness, we often take drugs and medicines in capsular format. Similarly, we can incorporate capsules into our matrix, ensuring that there's either homogeneous or localized repair of any cracks formed. When we break a bone, we have a knitting of our bone, a repair of our bone. Incorporation of bacteria or self-protected bacteria into our matrix allows carbonation and thus the knitting of the cracks. And we're often advised to have a balanced diet, ensuring that we have enough nutrients to have a best way of life. Similarly, we have an optimized mix design, making sure that the concrete or cement mixture that we're creating or developing suits the different applications that it is going to. So we talk a lot about these about these self-healing methodologies, but why do we not further see them within industry? Well, industrial demands are quite extensive, from the different loads that these structures must bear to the different environments that they face, the longevity of the structure required, as well as ensuring sustainability of the materials that we're introducing, healing efficiency, and of course, economic viability of the industry which we're entering. Only once these demands are met will we see a further integration of our self-healing methodologies.
Right. Although there are many research about self-healing cementitious materials to satisfy those aforementioned demands, this new system has not been widely used yet. Well, in any new system, there are a lot of concerns like uncertainty, lack of data in numerical or experimentally, the interaction between the new healing agent materials and the materials in the cementitious composite, as well as the compatibility between them is still unknown. Furthermore, the long-term behavior of the self-healing materials and their durability requires further research. And moreover, there is no reliable models to allow engineers to design their own structures with these materials. To address these concerns within the SmartThings project, as mentioned earlier, we have 4 work packages: improve the self-healing concrete, the advanced local application of the self-healing, like repairing and new technology for self-sensing this material. In the work package 3, assessing the durability and life cycle of the self-healing systems, and finally commercializing this product. Specifically, in the work package 1, we will investigate in 3 different self-healing scenarios and their material, like vascular network, macro and macro encapsulation systems, bacteria, and then how we could mix them and create a solid concrete. And finally, we need to model and simulate the behavior of the system. Well, our aim is to improve, optimize, and develop, improving the healing efficiency and healing materials behavior for each of the self-healing systems, optimizing the manufacturing process for those self-healing systems and any devices required for those materials, like optimizing the geometry of the vascular network or optimizing the process of manufacturing microcapsules, as well as optimizing the amount of each of the components required for concrete. And finally, develop it to make it usable for any kind of applications. Well, each of us will be working on different tasks. And Yasmina would be working on the optimized vascular network. Claire would looking for advanced capsule manufacturing technique. Mert trying to develop compatible bacteria for self-healing systems. Harry will looking for the optimized mix design, and Sina, myself, will try to simulate the self-healing behavior. Right. When you have all of the self-healing material and you want to add it to the concrete mix design, you need to consider the interaction between this new material and the cementitious existing components, like aggregate water and other material in the concrete. And also, you need to identify the required amount of each of those components, because this new concrete is rather different with the conventional ones. So you need to identify this amount of component to achieve certain concrete with specific properties. So to address those issues, within the SmartThings project, we will be looking for the different self-healing agent, which would be produced by RESRs as well as some other self-healing agent to commercialize self-healing agent, to consider different types of healing, to looking for any potential of the compatibility issue, or investigating the water-cement ratio, and also investigating the effect of capsules on the particle packing, or finding the void ratio due to the microcapsules. Within the consistency test and time-saving test, our initial results shows that with the different dosage of the self-healing and with the different types of self-healing, and based on which type of cement we are going to use, the amount of water-cement ratio would be different. So it shows the importance of finding a compatible optimized mix design. Now we are looking for how we could improve and developing the different self-healing systems.
Okay, great. So like Sina said, one of our first self-healing methodologies that we'll discuss today is the integration of a vascular network. Here we represented very simplistically with just a cylindrical tube. And some of the parameters which we need to take into account when assessing this vascular network and its applicability is the shape, the material of both the outer shell as well as the inner cargo, as well as the arrangement within the cementitious matrix. Here you can see a sample test rig, which uses 3 parallel cylindrical tubes to do just that. So when we're looking at it within the Smartings framework and the methodology of Smartings, how we're going to further expand upon this is look at the different wall material and shape that we can use with 3D printed vascular networks. An example of such you can see in the bottom left-hand corner. Furthermore, we're going to look at different healing agents throughout the vascular network, testing their efficiency and their applicability to this type of self-healing methodology. Moreover, we're going to ensure that throughout we are prioritizing healing efficiency and the sustainability of this methodology. Some initial results you can see in the left-hand side graph. We have different types of healing agents that have been tested, from 2 different types of water repelling agents, 2 different polyurethanes, and an epoxy resin. And you can see the clear benefit of introducing these healing agents when compared to our top line, our reference sample. And you can see on our right-hand side, the load regain plot when we introduce epoxy resin into our sample. So we load the sample with our 3-point bending test, introduce our healing agent, and then load again, and we see the benefit there. So moving on to a different type of self-healing methodology, we have capsular additions in which we integrate them into our matrix. We have some sort of damage, which then ruptures our capsules and initiates a restoration or healing response. However, within capsular design and integration, there are myriad different parameters that must be taken into account, from making sure that you have the correct formulation to homogeneous integration to no detriment to the mechanical characteristics of our cementitious matrix to effective triggering and healing effect. So keeping all of these things in mind, when we look at the Smartings approach or methodology, we're really trying to optimize our formulation as well as our production, and thus being able to scale this up further. We're expanding our materials, both looking at different shell materials and cargos and how this will suit our optimized formulation and scale up, and then ensuring that throughout we have effective triggering and healing and or corrosion inhibitory response. So I just want to draw your attention to the diagram on the right, membrane emulsification, which is micropore's specialty, and it is how we'll be furthering the optimization and scale up, in which a disperse phase, which later becomes your cargo after a further encapsulation step, is pushed into a continuous phase. You can see the membrane emulsification in action in the Cambridge laboratories here, highlighted in yellow. That is the membrane emulsification unit. So looking at initial results, a lot of time has been spent looking at the systematic testing of membrane emulsification, seeing how different operating and phase parameters may vary the type of emulsion and thus capsules that you're forming. This can be seen clearly, for example, on the right-hand side, where when we are producing polymeric capsules via stir-bar, a very basic experiment, you could say, or basic method of formation, compared to the membrane emulsification, that you have a much more homogeneous capsule formation with a much tighter distribution. So moving on, we've talked about a number of different biomimetic approaches, but what about purely biological? And Professor DeBele was talking about this before in our previous presentation. So when we have biomimetic, we use a manufactured device with some sort of chemical content that is then further physically activated to release this content. Looking purely at biological approaches, we have no external device. It contains purely itself and is often chemically activated. The Smartings methodology for these biological approaches is self-protected bacteria. So you can see in the bottom right-hand chart, we have a number of different biomasses that have been currently tested in different mix designs. And when we're testing them, we're making sure that we look at cyclic healing ability, making sure that we see effective corrosion inhibitory responses, and of course, prioritizing commercial viability, when introducing this into the cementitious industry. So looking at some of the initial results, you can see at the bottom left-hand corner, the compressive strength of samples does not decline when introducing our different biomasses compared to our control. Furthermore, when you look at the right-hand side, you can see how the flow value of our samples differs when introducing our biomasses or bacterial additions, and how this can then lead to further knowledge about how to optimize our mix design when incorporating these bacterial additions, as well as perhaps optimizing further additions. Yes.
Okay. Well, when you have all of those self-healing system and improving and developing the self-healing materials, and then you want to design your structure with these systems, there would be some questions. Which of those self-healing systems would be a better option for your application? How much of the self-healing material I need to use? And where I should put those self-healing materials? Should I put this self-healing system all of the entire structure, or not just a specific point would be adequate? To answer these questions, we need to find a reliable model which could predict the potential of the damage as well as the healing efficiency of those systems. And moreover, we need to identify the initial elastic properties of this self-healing material, and more importantly, the nonlinear behavior, because these properties is the most important and initial properties for designing structures. But is there any model in the literature to find to simulate the behavior of the self-healing systems?
Sorry, my screen is just, oh, there we go.
Well, there are a few models in the about the self-healing systems, but most of them are empirical based, which means that they gather some data and feed the curve to the data. And well, at the first glance, it might seem that this is the best way because it is based on the experiment, but this model would be available and validate within the experimental range, and out of the experimental range, it's not going to work. So it's always is scale dependent, and its output is the force versus displacement. And well, concrete as a heterogeneous material is complex, and when we adding some different healing agent, it become more complicated. So we need a further mechanistic approaches. So
I'm sorry, Sina, my screen keeps freezing. You can just bear with me. I might just stop sharing for a second. Okay.
All right. Well,
Sorry about that.
Well, so we need a more mechanistic approach for modeling this self-healing system. So within the smart things, we would be follow a coupled multi-scale approach, which means that we are going to the macro scales and considering the cementitious as matrix, adding our macrocapsule or macrovascular network as an inclusion. So within the macromechanical formulation, we could calculate the elastic properties of this system. And then when we applying load, we could anticipate the crack initiation and its effect on the overall response of the cementitious matrix. Then we adding the healing event and healing mechanism. And so we could simulate the overall responses when we have healing. So after that, we apply this material to a proper element within the macro scale. After we improving the accuracy and the range of the applicability of this model, this could be implemented into the current code and guidelines. So then engineers could use these models to design their structures with this material. And what exactly we means about the coupling our model with the chemical and physical process? Well, as an example.
So sorry. I don't know what's happening to my computer.
Do you want to share my screen?
Perhaps that'd be best just for the final slides, yeah.
Okay. Could you see my screen now?
Yes.
Okay. Well, consider vascular network when we have crack initiation, and then when we applying load, the vascular network, the vascular tube would be broken. So the healing agent transport through the crack, and after, so this would be a physical process. And after that, after a certain time, the healing agent would be cured. So this is a chemical process, and some experiment shows that an exponential function could capture the curing function of the healing agent. So we have the mechanical regain behavior, and based on the types of your system, whether it would be a single healing event or rehealing, redamaging system, you could anticipate the behavior of the self-healing system, which you could see in the right-hand side figure. So until now, we show how we could improve and develop different types of self-healing systems and how we are going to simulate its behavior. Now we are looking to collaboration potential within this work package.
Yes, so within Work Package 1, we have some key examples of collaboration. Firstly, looking at the different self-healing cargoes between vascular networks and micro and macro capsules. So ESR1, Yasmina, and myself, ESR number 2. Secondly, Sina will then further model these capsular and vascular additions, taking into account as well the work that Harry does with the optimized mix design, incorporating various different capsules as well as self-protected bacteria. And last but not least, Sina will also incorporate self-protected bacteria and its self-healing methodology into his model, excuse me. Okay. And then within Smartings as a whole, there is, of course, collaboration as well. So we've discussed the various different types of self-healing developments that we hope to optimize and further develop in Work Package 1. This will then go on to Work Package 2 to look at the various different applications of these self-healing methodologies, as well as looking at Work Package 3, where durability, longevity, and the lifespan of these developments will be assessed. Last but not least, Work Package 4 will hope to commercialize these methodologies as well as their applications using the durability and lifespan and sustainability data generated by Work Package 3. So thank you all very much. I'm very sorry for the technical difficulties that we had during the middle of the presentation, but I hope you learned a little bit more about the various different self-healing methodologies that currently exist, as well as the Smartings approach to optimize and further develop them. Thank you again.
Okay, thank you, Sina. Okay, thank you, Sina and Claire, and sorry for the echo. I have not yet received any questions in the chat, but considering that we are running a few minutes behind, if anybody has any questions for Sina and Claire, please ask them in the chat.